Hello everyone, my name is Brianna Curl and I will be your moderator for today's webinar on selecting PCB materials, electrical and manufacturing considerations. If you have any questions throughout the webinar, please type them in the questions panel as they come up. We will have representatives ready to answer your questions directly during the webinar. This webinar will be recorded. The recording and the presentation slides will be posted on the EMA resource page. Today's webinar is hosted by EMA Design Automation and Sierra Circuits. EMA Design Automation is a leader in product development solutions, offering a complete range of electrical and mechanical CAD tools and much more. Sierra Circuits has 30+ years of PCB manufacturing and assembly experience, which has made them the trusted source for end-to-end PCB prototypes. With that being said, I want to thank you all for joining us for today's webinar and introduce you to our presenters, Amit Fall and Matthew Harn. Amit has been in the PCB industry for 20 years. He is a director of sales and marketing at Sierra Circuits. His passion is to empower tech companies to achieve their visions and change the world. Matthew Harn is an electrical engineer from Canada and has been with EMA as an application engineer since 2003 and as the application engineer team leader since 2018. At EMA, he specializes in design side issues pertaining to part management, circuit simulation, signal integrity, and power integrity, but is conversant in all facets of the ECAD design. Amit will start off the webinar with a presentation, followed by the demonstration given by Matthew. Assuming we have time at the end, we will field some questions in a formal Q&A. Thank you for your attention, and now over to you, Amit.
Yes, thank you so much. Thank you, EMA, for hosting this webinar. I'm very excited about being able to collaborate both a little bit in theory as well as the design tool and then actual manufacturing. I think it's going to be a great webinar, and so we welcome everyone's questions. There's a lot of material to cover, so if it's not covered today, hopefully we could do more webinars with EMA and we'd be happy to address those things going forward. I definitely want to talk about PCB stack-ups, the basic properties of dielectric materials, which is a little bit of motherhood and apple pie, but still important. And then, I break up the materials a little bit into different categories based on signal loss and operating frequency. And then we talk a little bit more about copper foils and then, some best practices in selecting, your materials and some stack-up considerations as it pertains to HDI. Okay, so PCB stack-ups, they're the most, as far as a manufacturer is concerned, something that's super important in building a reliable circuit board, in building a cost-effective circuit board, and then from an electrical standpoint as well, building, a circuit board that functions the way it's supposed to. So there are some general guidelines. You want to keep your stack-up symmetrical, so that's ease of manufacturing, so it doesn't warp or become a potato chip. And we'll go into the next slide, which is like, what are the ingredients for PCB stack-ups and PCB materials? So it starts off with pre-preg copper foils and core materials. All are important in your design considerations. So pre-preg is B-stage material that is tacky and allows for bonding of the different foils or laminates. A copper foil is, obviously for your traces and your pads. And then your core material basically is pre-preg that is already melted or C-stage, and there's copper foils already, laminated to that core. So all those are very important ingredients to your stack-up, as we'll talk about later. So each material itself has these thermal properties and electrical properties. So when you're picking a material, kind of the first considerations are, what are the, actual properties of the material. You should definitely not stop there, but this is a good place to start. So for glass transition temperature, it's basically where the PCB substrate material, goes from a glassy rigid state to a softened state. So that's important if you're in, higher temperature swing applications. So here are some basics. 370HR has a TG of 180. Rogers has a TG of 280. Next one is the decomposition temperature. So basically, at what temperature the material decomposes chemically. And so you can see again, like 370HR versus Rogers. you want to make sure that if you're in a, an application that needs to remove the heat, the material can play an important role in that application. So low thermal conductivity means low heat transfer, while high conductivity implies, higher heat transfer. And then last but not least important is the coefficient of thermal expansion. It's the rate of expansion of a PCB material as it heats up. And so this can be a very difficult situation if CTEs of different materials, don't match up. The CTE of copper, the CTE of via fill material like a SANA or a silver fill, CTE of your component packaging and the solder joints, all that plays a role for the life of the product. Okay, and then electric properties, dielectric constant, dk or ER, which mean the same thing. So in this, it's really important to understand data sheets are actually not correct. They're a good place to start, but they're usually only valid for a specific resin content percentage, usually about 50%. And actual resin percentage in a core prepreg really varies based on composition, and it changes after lamination when you have a press out thickness, and that press out thickness is based on your copper percentage. So there's a lot of things that vary the ER and the DK, so it's really critical for your manufacturer to help you calculate that for your specific stack up. Okay, so loss tangent, or the dissipation factor, is the tangent of the phase angle between the resistive and reactive currents in the dielectric. The dielectric loss will increase with the increases values of the DF. So low values of DF result in a fast substrate material, while large values result in a slow substrate. So the DF increases slightly with frequency. So for higher frequency materials with very low values of DF, it has very low variation with the frequency. So that's the value there. Signal loss and operating frequency. So this comprises of dielectric loss plus the copper loss. So signal loss causes signal attenuation. That's why this is important. Dielectric materials are made up of polarized molecules. These molecules vibrate in the electric field generated by time-varying signals on the signal traces. This heats up the dielectric and results in dielectric loss, part of the signal losses. So again, signal losses increase with frequency. The loss can be minimized by using a material that has a lower dissipation factor. So copper loss is also part of the total signal loss, and a little explanation there is due to AC resistance of the signal trace and the applicable return paths. You can have an increase with frequency due to the skin effect. So copper foil dielectric toothy interface provides the increases of the effective length and thus increases the copper loss. So picking the copper material and the toothiness of the copper material has an important role to play in your total signal loss. So basically use low profile copper foils. And so you can specify that to your manufacturer if that's important in your application. So this slide is, the correlation between signal loss and operating frequency. So signal loss or attenuation increases with the frequency. And, with this data, you can see materials kind of naturally group themselves together. Which material could you possibly choose from, which would perform better electrically at higher speeds? That's kind of what this is showing. So of course 370HR is the worst performing material here. Then you get down into the Nelcos and the Rogers like that. So to me, it breaks down into, you have these kind of categories for materials. So in the normal speed materials, most common PCB materials or the FR4 family, the dielectric constant versus the frequency response is not very flat, and they have a higher dielectric loss. So I would say suitable for 2 gigahertz applications. For your medium speed, medium loss, and higher temperature materials, you could go with something like a Nelco N7000-2HT, and still suitable for roughly around 2 gigahertz, maybe 2 to 5. And then you have your high speed, low loss materials. A good example of this material would be an isola high speed that can handle, in the 20 gigahertz range for your applications. And really what you get is, less unwanted electrical noise. Okay, then you have your materials for your RF or microwave applications. 5G is an example, suitable for 60 gigahertz applications. And an isola material that would be good here is a tachyon. Again, just grouping the materials a little bit so you can kind of see from a different perspective how it looks. These are the materials that we work with every day. So if you find yourself trying to pick a specific material, you should definitely talk to your manufacturer, understand what they're comfortable with, what they've manufactured before, because every material is different per different manufacturer. But these are the standard materials that we prefer. This presentation is not about flex, but we have put through in some flex materials in there. If you want a presentation or a webinar on flex, we can arrange for that. So going through the copper selection, so we talked about copper foil a little bit. So it does play an important role in your stack up and in your electrical performance. Basically, copper thicknesses, vary from 1/4 ounce to 1/2 ounce to up to, let's say, 4 to 5 ounces. So 1 ounce of copper is about 1.4 mils of thickness. So when you're getting into the 3, 4, 5 ounces of copper, realize how thick that's going to, make your board or contribute to your board. For copper purity is the percentage of copper found in the copper foil. Electronic grade foil has a purity of around 99.7%. And we talked about the interface profile already. For high-speed applications, you really want a low profile. There's also electrode deposited copper versus rolled and annealed copper. Rolled and annealed copper is used for flex application. You do not want a plate on top of your flex layers. You do what's called a button plate. So you're only plating in the via and not on the surface. So PCB material selection best practices. I think this is, why most people are here at this webinar, is to hear, what issues to avoid, what should I really consider? And so we talked about it. Material selection is really important for the electrical performance as well as manufacturing. So, with materials, look at the DK, look at the CTE, look for specifying, a tighter weave for glass, because you get into a situation where it performs better electrically. One practical example, we were building a board for imaging, and it was a very tiny application. I think it was a dental application. And, the board was working perfectly with one material type that had a very tight weave of glass. And so it performed well electrically, but the cost of the material was a little higher. And when the when the OEM switched out that material for something less expensive, the product wasn't performing as well anymore. So, these types of decisions actually affect how the end product will function. One example for moisture absorption: if you have a really big board and high layer count, moisture absorption is an issue at assembly. It's an issue. It changes the, how do you deal with the product in manufacturing, and it can cause lots of issues with pick and place machines, with components, I would say, exploding during assembly, and like all those types of things can happen. So if you have those applications, really consider on lower water absorption material. Okay, so how do we achieve the best possible PCB stack-up design? So consider, what is your application? So whether it's an HDI or standard stack-up, you need to follow certain guidelines that are just best practices. So first is understanding how many signal layers and power planes you would need. So your stack-up is truly dependent on the number of signal layers. So if you have a lot of high-speed signals or a high-power application, you're going to require more layer counts compared to lower speed applications. And that's totally okay. It's just the nature of the beast. If you're routing analog and digital signals, you definitely want to separate those out sufficiently so the digital noise doesn't enter into the sensitive analog signals. So that could also change, your stack up design. And then low pitch, high pin count, complex devices like BGAs, of course, they require a greater number of signal layers. You should have a strategy for breaking those out. And then, so if you have special signal integrity requirements as well, and you want extremely low crosstalk, this will also lead to an increase in the number of signal layers. So actually, lastly, you want to consider how many ground and power layers you have. So the use of ground and power planes allows for the designer to allocate signal layers purely for signal routing, which can reduce the DC resistance in the power and ground rails. And this would ensure less DC voltage drops in the devices. So there are some advantages to taking that strategy in your layout and your stack up. A couple more points actually on the ground layer. So that's obviously where you're going to connect your power supplies, and the power supply is a flat plane of copper, usually in the PCB, connected to the power supply rail. And the planes also provide signal return paths for the varying and high frequency signals, and it helps considerably reduce the noise and signal crosstalk. So those carefully placed are really important to get good signal integrity. Kind of in summary, the significance of a PCB stack up, it's a good stack up will reduce your electromagnetic emissions, crosstalk, and improve your signal integrity. It definitely controls the impedances of the traces. You can reduce the size of your PCB. You can, control your routing density. So these are all the, kind of significance of PCB stack ups. Of course, having low noise ground and power planes, these are all super important for PCB stack ups. So here is a typical 10-layer stack up, ground layers for each signal layer. Totally okay to do. In this stack up, I just wanted to kind of illustrate, we have a column at the final thickness. It's on the right. That's again kind of pressed out thickness. We are showing copper percentages. We're showing which are the plated layers. So in a sub construction, you might have more than just 2 plated layers, more than just the outer layers. Your inner layers can also be plated, so be careful of that as well. And so here's a quick example of an HDI stack up. So here, HDI is suitable for fine lines and tight microvias, those type of things. And you can see, when you pick your HDI dielectric, you have to be especially cognizant of the fact that you're going to laser through those materials. So actually having good material selection there would be very important to properly form your laser vias, and then therefore get good plating in those vias, and therefore having a more reliable HDI board. So these are some of the key considerations for HDI. I mentioned laser drilling. You also want very dimensional stable material because of all the process steps that you have to kind of go through for HDI. And here's another kind of stack up for HDI. And, just as a kind of a summary, when you're sending over the data, we still get people who get this wrong. If you want to send this over your native design database, go ahead, but that's a lot of IP in there. And I still think it's a good idea to send over just, the ODB data. And if not ODB, send over Gerbers with your IPC 356 netlist so that we can make sure that there's no issues with the outputted Gerber data. But these are the files you need. That's the kind of the theory part of the presentation, and it's really important that your CAD tool is aware of all these things for manufacturing. And so I wanted to kind of hand that over now to our partners in crime and have them walk through practical examples on how to manage your CAD tool with that.
Thank you, Amit. And at this point, I'm going to pass it on over to Matthew for our demo portion.
Thank you, Amit, for your presentation. That was super interesting. I was especially interested in the exploding components. That's what I wanted to know more about. So very, very interesting stuff throughout. I really appreciate you showing that. Amit did mention, and he had a link in one of his slides to a material file that he is able to send, or Sierra Circuits is able to send to to you. I have it displayed here, and I'll use it a little bit as reference here in the demonstration today, but just wanted to show you how we can take some of this material data and make it present in the PCB editor tool. So we're showing the Allegro PCB editor tool, same as OrCAD PCB editor tool. Same thing if you're confused about the differences between those. But here's a number of materials that Sierra has given to us and their characteristics. So you have your dk, or your dielectric constant, you have your df, which is your dissipation factor. We call it loss tangent in our tool. So we'll see those, and we can enter those for the different materials into our materials database. So after picking the material, consulting with Sierra Circuits, figuring out which material is going to be best for your application, you can then enter those material data into the PCB editor tool. So moving to the PCB editor tool, here's the Allegro PCB designer. In setup, you have the ability to start assigning materials. And these are, what I'm showing is the materials that just come with our software. So many come with them. If you decide that you want to use Sierra Circuits materials files, you can update some of this data. I imagine it'll be slightly different, their data, than our data. You probably would want to use theirs. I would suspect that theirs would be more accurate because they're more familiar with their manufacturing process. Ours is a little bit more general. So I would certainly update your data here to reflect what they have, but here you can see some materials that you have and some that are being used in our design. So in our case, it's air and copper, and FR4 is in our design, but we can change them out for other types of materials. I think I have a polyimide in here somewhere right here. So you can use one of those if you want some of those higher end materials that have lower losses associated with them for higher speed signals and potentially RF signals. You might want to use some of those types of materials. And we'll show how to change some of the materials around that we have. So this is the available materials that we have to work with. And if we want to start working with them, here I have a board. And in this board, I want to start taking a look at my stack up. So you're going to enter your stack up by hitting the stack up button. And you're going to see a bunch of data here. Similar to Amit's slides, you see your stack up graphically over here on the right-hand side, and you can zoom in and get a better look at that if you want to. You can see your layers specifically over here, the names of them, what types of layers they are, and what function they have. You can see the thickness of those layers, and again, as Amit said, you want to be careful as these numbers do add up. So you want to make sure you're taking it into account how thick those things are actually going to be. If you're using thicker copper, that's going to add to your overall thickness, of course. Copper and FR4 are the materials that I'm using right now, and I'll show you how you can change those. It's just going to be dropping down and picking a different material from our materials file that I'd shown you previously. So if you do want a different material, you certainly can do that here. For now, I'm just going to be working with copper and FR4, and I'll show you a few things that we can do around impedance. So I'll just start this conversation talking about impedance and what we're going to do with that. So I've opened up this signal integrity wing in this cross-section editor tool, and that's what we're seeing right here. And we get to see a bunch of information about our impedance is something that can be quite important. In our case, we have top layer impedance that we're going for of 60 ohms and some internal layer impedances here that we're going for 60 ohms. What if you wanted a different value? So if you're desiring 50 ohms, for example, you can edit this and it's going to edit your width accordingly. So if you wanted 50 ohms instead, you need a very thick 21 mil trace. You may want to change some of your layer thicknesses or materials instead of routing a net that's that width. But by playing around with this number, this impedance that you want to get, it's going to give you a corresponding width in mils that you want to hit. And what I've done here is I've entered an impedance of 60 ohms, which is great. Width of 15.201 is probably not something you're going to want to hit precisely. You'll maybe want to go for something like 15 instead, and then you can see what the impedance is going to change to because of that. So if we want to just keep this in the back of our mind, we have a 60 ohm single line impedance that we're trying to hit on our top layer. And to achieve that, we need width on our trace on the outer layers of 15 mils. So we're just going to keep that in our head. I'm going to come back to that a little bit later. Let's do the internal layers next. So in our stack up here, we want 60 ohms maybe again, so we can hit 60 here. And it's going to change this to 8.89. We can maybe change this to 9 instead of 8.89, or maybe even something a little bit off. So 9 is very close, but maybe 10 mils would be more achievable for our process or more desirable, and we're okay with an impedance of 57. So we can enter 10 mils then as a constraint for our inner layer here for this one and for this one as well. We can verify that 10 is going to give us the same impedance. There's symmetry in our stack up, so it's going to be the same for this layer and for this layer. So that's how you can start achieving your impedance and just figure out some ballparks for where you need to be. On the bottom half of the board, what I've done is I've tried to hit 50 ohms. And this is probably not something you're typically going to do on your boards, but I just wanted to do it within one design where I could show you how you can hit different impedances on different places. So if we had said 50 ohms down here, we can see that there's a line width on the outer layers of 6.524. Let's round that to an easier to use number, 6.5. And again, we're going to keep that in our memory. So outer layers for 50 ohms is 6.5. And for inner layers, we can do the same thing that we just did before. So we'll say we want 50. That's going to be about 4 mils. That might be a bit tough for us to achieve. Maybe we want to just go with 5, and 46 ohms is close enough, so we can do that. So you can kind of play around with this. You can balance different things. There's going to be a lot of riding also on the materials that you pick. So in this case, I'm using FR4, but if you want to say, well, I need to try some different materials, I'm not able to achieve physically what I need with the materials that I've had, you can go to some higher quality materials, and you can see you're able to lower your impedance a lot just by choosing a different type of material here for that. So if lower impedance is something that you want, maybe a different material type would be appropriate for you, but you can definitely play around with these and find the balance of what you want compared to what you need to get. Over here, I'm just going to close the loop on differential impedances as well. So your differential impedance is one thing. We've been talking about single-ended impedance so far. Differential, we might also want some amount of control over. So if we want 90 ohms at the top, we can type in 90 ohms right here. And the tool is asking us, what should I change to make that happen? Do you want me to change the line width? In this case, we don't really want the line width changed because it's needed to achieve our single-ended impedance. So let's change the line spacing instead. So I'll hit OK, and it's going to go through and do a little calculation and update the differential spacing. So if you have differential nets on the top layer that are 7 mils apart with 15 mil widths, you're going to get a differential impedance of approximately 90 ohms. And you can do the same type of balancing thing for the rest of these lines. I'm not going to continue to go through this, but what we want to note here is that the outer layers are about 7.5 and the inner layers are about 8. So we'll take those numbers. You don't necessarily need to remember them. I've got them in my head. So I'll show you what we're going to do with those numbers next. But what we wanted to show here is just how you can take a look at some of the materials you can put them in, play around with your widths and your spacings to get some of those different impedances. And those are all based off your dielectric constants and your loss tangents that you received from CRS circuits. All right. Next, let's take a look at how we apply these rules, if you want to call them that we've come up with. So we've come up with some rules here, and we want to apply them to our design. And the way to do that in PCB Editor is to open up the Constraint Manager. And in the Constraint Manager, we're going to go into physical, and we're going to start entering some general rules. So we'll start with the 50 ohm, we'll start with the 60 ohm one. So that was the one that we did on the top part. And if you have a very good memory, you'll remember that I said our spacing, our line width on the top, or the external layers, is going to be 15 mils. And on the internal layers, it was 10 mils. So that's what we're seeing entered here. We've entered this as a constraint. So the rule is 60 ohm single and 90 ohm differential pair. So if we want 60 single, 90 ohm differential pair, this is the spacing width that we're going to need to achieve that. So 15 mils external, 10 mils internal. And we can also see the spacing for that as well. So if we scroll to the right, I went too far, you can go take a look at the differential pair. So our gap here is 8 mils, and that's on the internal layers, and on the external or the outer layers, that's 7.5. So those are numbers that we got from our analysis that we were just doing in the previous step. We've now entered that as a rule for our 60 ohms. And with that rule now present, any net that we apply this rule to will have those restrictions where the nets, the width and the spacing will be whatever we described right here in this rule. We're going to do exactly the same thing for the 50 ohm net. And I'm not going to go through this in gory detail, but we had 8 and 7.5 mils. And then on our spacing, we had, right over here, we had primary gap. Oh, sorry, that was our primary gap, 8 and 7.5. And our physical was over here at 5 and 6.5. So those were the rules that we discovered from playing around in the stack up. what we then did, and I'm not going to do this live, but what we then did is we routed those nets. So we routed a collection of nets. These ones on the left are 60 ohm nets. These ones on the right are 50 ohm nets. And they should be routed then with the width and the spacing that they need to achieve their impedance. And you can see in here, we are going to have some exceptions, of course. So as you come out of some tight ball patterns here, you might need to loosen those restrictions up. We call that neck mode. And the other thing that you're seeing in action here, in case you've ever wanted to do it, is something that we call snake mode. So you can also snake through this to get through areas that would otherwise be hard using traditional harder corners. Those might not be areas that you'd be able to escape out of using traditional techniques. So we have snake mode to get out of there. We have neck mode to make the traces a little bit tighter, and that allows us to escape our pattern, and then we can go out here, we can release those restrictions and go to regular routing mode, where we're then going to be able to hit our impedances that we want. You can also verify these impedances as well too. So if you want to verify them in the board, you can do that by, I'm going to just query one of these nets. So I'm going to open up the Constraint Manager one more time, and I'm going to query one of these nets and take a look at it in the impedance. So in the Constraint Manager, you can come here and you can give it some routing and impedance constraints. So you can put impedance constraints on your net. Let me just grab that guy one more time, and it should pop up hopefully for me. There it is. So what I've done is I've put some impedance constraints on this net. This was on my 50 ohm side, and I've given it a target impedance of 50 ohms with a 2 ohm tolerance is what I've done on that net. And what I can do is I can now check against that. And I have been the whole time. I just turned the visibility of that off. Let me turn it back on. And you can see what has happened here in this case. So this net, as it's routing, we're getting a bunch of impedance DRCs here. We're not hitting our impedance in this area. And that's known. We're aware of that because we were necking down to get out of that device. And over here on the 60 ohm side, I did the same thing over here. We're getting a bunch of impedance violations over there as well too. Notice that those violations go away once you escape out, and you no longer see those violations. So you are meeting your 50 ohm impedance for this side and 60 ohm impedance over on there on that side. Another way of looking at impedance, if you wanted to, so that's one way you can enter it as a constraint if you want to. Another thing that you can do is you can do analysis on that. So what I'm going to do here is I have a different board, a few more nets assigned on this one, and I'm going to do this live. And this is just a regular board. I don't have any pre-compiled results for this. I've just selected a pile of nets right there, and I'm going to hit Start Analysis. By the way, how I got here is I got here under Analysis Workflow Manager. So if you'd like to try this yourself and you have the professional level OrCAD PCB editor tool at a minimum, you should have this available to you. So an Analyze Workflow Manager. And I just selected the nets by hitting Select Net, grab the nets. I'm going to hit Start Analysis here. That's going to take about 30 seconds to run. So I'll talk through while that's running what's going on. What the tool is doing, and again, there was no setup required for this to work how it is. There's no models assigned. This is just your board brought into the tool with the net selected. And what it's doing now is it's calculating the impedance for all those net segments. So every net segment gets its impedance calculated, and it's going to be reported back to us in what I find is a visually very compelling way. So you can do what we call an impedance vision. So that analysis is done. Those nets impedance has been analyzed, and you can now look at these nets and see the impedance of those nets as a function or as an overlay on top of the net themselves. And you can see some interesting things as you're going through here. You can kind of almost see like shadows of something that's happened here. There's a line that's going across here that appears to have a different impedance. There's another one here as well too. And up here we've necked down to get into our components. You see the impedance change there as well. And here's some more kind of ribbons of discontinuity. What's actually happening there is we're going over a reference plane, and it's causing that problem. So I'm just going to brighten up some of the other layers here a bit, and you can see some of those other planes where the signal is traveling adjacent to, and the impedance is changing because of that. So that's something else that you can visualize. I wanted to point out just how easy it is to do that. So you can open up your tool, run that impedance check, and just do kind of a sanity check and make sure that your impedances are good and that you don't have anything way out in left field that you're unaware of. So you can do a quick check. It's almost like spell checking in your Word document or on your email. Just a quick check to make sure that everything is going well. All right, I have two more things to show, and then I'll open it up for one more polling question. So the other thing I wanted to show is just how backdrilling works. So in backdrilling, What you can do is you can have your pad set up. So here's a mini back plane here that we're looking at. And what we want to do is we want to backdrill some of these vias. The reason we want to do that is to get rid of that piece of metal that's going to be a stub on our via. So it causes signal integrity issues. We want to drill that out, just physically remove it from our board. And that's something that we're able to specify in the design tool. The way that you do that is in your pad stack, you're going to say it's allowed to be back drilled, and then here you can verify what's actually happening in that pad stack. You can just select, I've just selected any one of these, I believe all of them have back drills. And I'm going to hit edit on that pad stack, and it's going to pop up the pad stack editor for me. So here's the pad stack itself, but what I'm seeing is I'm seeing a secondary drill. So the secondary drill is actually back drilling, removing the copper of that via from some external layer to some internal layer by some distance. And the tool is able to figure that out itself, how far it needs to drill based on the layer that it's coming from and going to. It knows which type of back drill to use to make that effectively work without ruining the trace that you're trying to still use. Where that's set up, so this is how you can just visualize that it's happening and verify the distance that it's drilling. Where that back drill is all set up is right here in backdrill setup. So in backdrill setup, you can set up your from and to layers. So you're starting on top and you're going to layer 2. That's what you want to backdrill. So you can backdrill from either the top or the bottom. And from the top, we have 3 different options of backdrilling. So we can go to the second layer, not cutting the third layer. We can go all the way to the third layer, not cutting 4P. We can go to 4P, not cutting 5. So those are our 3 options if we're drilling from the top. And from the bottom, we have from the bottom to 9P, 8, etc. You can read the rest of that. If you want to add additional layer pairs, you can. So you can just right mouse button, add a new pair set, and add another option for another back drill that you can use. Out of that, you can get some manufacturing data here that is pretty compelling to look at, pretty interesting data. So you have your core via that goes all the way through, and then you have a few of your top layer vias. Notice we only see 2 here because we're not actually using that third one. And we have a number here coming from the bottom up where they cut through a certain number of layers, but not through others. And you can see that graphically here, and then here's some of the drill legends that your manufacturer will be interested in seeing for some of those depths. And also it's going to be attached, it's going to be a drill file that they can plug into their machine so they know exactly where to back drill those out. All right, so that was back drills. Let's talk finally about the next option, which would be blind and buried vias. So if you're doing HDI type connections and you want to use some blind and buried vias, you can. I'll just zoom in here and show you a few that are on display. Kind of a neat thing that you can see here, I hope this comes across on the web clearly enough, but you can see the layer that a via starts on and goes to. So here you can see it starts on 7, goes to 8. Here's one that goes from 6 to 7, 3 to 6. And you can see the difference here also between a core via and a micro via. So a core via being these wider ones, a micro via being these littler ones here. You can set these up again in Constraint Manager. What I want to highlight is just a couple things, how easy they are to route. So if we do want to route with some of these blind and buried vias, you can just come off here. I'm just doing something not terribly useful, but I just want to show you how it works. And we can specify which layer we want to go to. So I'll have the tool ask me which tool I want to go to when I double click. Normally when you double click, it just toggles between the 2 layers you're working between, but here I'm going to have it actually ask me. So I want to actually go to, let's say, the bottom. From the layer I'm on, which is signal 4, I want to go down to the bottom, and it's going to do that. So it pops in first my 3 to 6, and then it's asking me where I want to put the other ones. 6 to 7 is down there, and now I'm on the bottom. So if you do want to see that put in there, you can go choose to go to the bottom, and it's just going to kind of daisy chain those blind and buried vias together. And you can have all sorts of settings. If you want to allow these to just stack right on top of each other, that's certainly something you can set in the tool. In my case, I chose to have them offset. So you see 3 goes to 6, 6 goes to 7, 7 goes to 8, and by then we're on the bottom layer using some micro vias. If we do want to take a look at this, also more visually, you can view this in the 3D canvas as well. So this is a pretty interesting way of looking at this. And what you can do is, let's see, we want to turn off some of our layers. So let's turn those off like that. And then you can view the stack up. There's those vias that you can see here, but you can see those vias and the traces that come with them in 3D as well too. So some really neat ways of looking at data, some interesting ways of putting this together so that you can ultimately generate good data that's going to go to your manufacturing house. So I'm going to pass it back to Brianna for one more short time for Q&A.
Thank you, Matthew. At this point, you can enter any questions you have as we go into the Q&A, and I'm also going to unmute Kanwar, who is a PCB designer with Sierra Circuits, and Attar, who is the general manager of their design and assembly divisions, to help us with answering some of your questions. And let's see, our first question, what about this in ORCAD or Electro? Can we assign the differential impedance, have a separate line width from the SE impedance?
No, I can answer that.
Okay.
See that if the differential impedance required is exactly the double of the single-ended impedance, then the trace width for the differential impedance has to be less than that for the single-ended impedance. Let me give an example. If you have 50 ohms at 5 mils and you want 100 ohms, then 100 ohms has to be less than 5 mil. Because if you choose 5 mil for the differential impedance, then basically it is theoretically you should require infinite separation, because those two lines will become actually virtually two single-ended impedances without any coupling. The whole idea of differential lines, differential pairs, is to allow some amount of coupling between the two lines, and therefore the trace width there is always different from the single-ended impedance trace, which is half that of the differential impedance. So the answer is yes, the two lines should have different widths.
Thank you. So our next question is, says, clarify for me the definition of back drilling as opposed to just ordinary drilling for vias and through hole pads.
The back drilling, basically what happens is that you have a, let us say you have a through hole via going from layer 1 to layer 12 in a 12-layer stack up, and your signals, that via is only meant for signals from layer 1 to 3. So the from 3 to 12, layer number 12, this entire height of the PCB, what you have is a VI stub, which will definitely create resonance and some very undesirable effects at very high frequencies. It will attenuate the signals at the resonant frequencies and all that. So idea is to basically back drill it so that remove the copper from there so that the stub length becomes very, very less.
So from a manufacturing standpoint, back drilling has become very mature. So there was also a question of when you back drill, how accurately can the back drill stop? So the back drill can stop within 1 mil of where you want it to. So the dielectric material, if you're piercing through all the way the copper and you don't want to hit the next copper layer, you know, your dielectric material can be like 4 mils, no problem, and the back drill can stop. But the back drill itself should be bigger than the original hole size so you can properly clear out that copper.
Thank you. So our next question is it possible to maintain the differential impedance in flex PCB?
Yes.
It's good to know. Let's see. We have a question here that asks, at what frequency is considered high frequency?
Oh, that's a very related question, but let us see how we can answer that. So the high frequency syndrome changes over time. In the, let us say, 20 years or 30 years back, even 100 megahertz was considered a high frequency. Today is about, we're talking in terms of gigahertz range. So about 1 gigahertz is considered high frequency. Less than 1 gigahertz is not considered high frequency, because our manufacturing technologies, our material technologies, and our modeling technologies all have basically progressed quite a lot. And therefore, we are able to manufacture more precise signal traces and have more control over material properties than we used to have 30 years back, 20 years back.
Okay, thank you. Let's see if we can get another question in here too before we run out of time. How does one decide thickness of pre-preg?
Thickness of pre-preg is generally decided by, let us say, the total number of layers. Basically, your question, a generalized version of the question is, how do you decide the dielectric thicknesses between various conducting layers in a PCB? So let us say you have a 12-layer board in which there are 12 conducting layers, and your overall thickness you want to be around, let us put it this way, 62 mils. So if you reduce from there all the copper thicknesses that you have, then basically you roughly can divide that by 11 dielectric layers which are there in between, and you will get an approximate idea of the average dielectric thickness you want. That is one thing. The another thing is the prepregs available. See, the prepregs are generally available from thicknesses from 2 mil onwards. Okay, and a very common prepreg thickness which is generally used between layer 1 and layer 2, especially when you want to have control impedance traces on layer 1, outer layer of 50 ohms and 100 ohm differential, then should be around 3 mils. If you model all those kind of things, depending upon the material decay, it will generally be ranging from 3 mils to 4 mils. But finally, so that is, of course, another thing is also prepreg thicknesses or any dielectric thickness also depends upon what is the application. If you are using a very high voltage board, let us say you have boards in which the the voltage across 2 layers can be as much as 1000 volts. In that case, it will be governed by the more governed by the electrical strength of the dielectric layer. Okay, so that puts another constraint on it. So the constraints on dielectric thicknesses are materials available. Number 2, the impedance heights are the modeling and the kind of trace widths you want. And if you are, let us say you are able to have a 3 mil trace for 50 ohms, you can as well do a 2 mil dielectric height. Of course, if you want don't you want to use less than 5 mils, then in that case your dielectric height can be 3 mils upwards and all that. So there are 3-4 factors in deciding the dielectric thicknesses.
Great, thank you. This is very informative. I'll ask this one last question here. Is there a differential impedance calculator they can use?
Oh yeah, we have, see, let us put it this way. We have a differential. Sierra Circuits has on its website a free impedance calculator, which also calculates differential impedance. The Allegro has a differential calculator inside it. And if, let us say, you ask any PCB manufacturer for a stack up and ask him for what is the differential impedance required, they can actually provide you the calculations. Sierra Circuits is also upgrading its impedance calculator to make it more accurate and totally in tune with the entire material database, which is being talked about by Matthew. So therefore, within 2 months, you will find an extremely powerful and good impedance calculator on Sierra website.
Thank you. So with that being said, we are running out of time, but I do see we still have a lot of questions coming in. So if there are questions that we didn't get to during the Q&A, we will be following up with you individually. I want to thank you all for engaging and asking so many questions. We will also be sending everyone a recorded version of today's webinar with the presentation slides within the next few days. And I want to thank you all for joining us, and thank you to Matthew and Amit and Achar and everyone else on the back end helping answer these questions. So with that being said, thank you, and I hope you all have a good rest of your day.
Thank you.